Okay. So anyway, largely the material through chapter 7 is all of what will be on the exam. But today we're going to, assuming you're happy with it, we're going to move forward into chapter 8 and 9, which is actually pretty darn good as a way of reviewing for the exam. But I like to sort of focus on making sure you feel comfortable with any concepts you've been studying up on or reviewing before we move into the chapter 8 9 content. And again, you'll see something in the lab today, assuming that you do the lab today, that you're going to say, oh, that's exactly like or quite similar to what we've recently done in the course material. Okay? So it is a bit of review, but we're going to move a little bit further forward as well. Before that, though, hey, got any questions? He says, looking at a few of you.
Is there an answer key for the fall 2006 practice exam?
Yes, there is. I have not put it online yet. I was
Oh,
going to do that tomorrow morning. And the reason is some students invariably say, well, I feel tempted to always look at the answers. And so I wanted, because some students in the past have requested, I want to honor that request. And I was assuming you guys would want that as well. The opportunity to practice some problems without the answers staring at you in the face. And then once the answers are available, you'll be able to look at them and sort of check your work, so to speak. One other thing I do want to mention is on the lab in chapter 6 and the lab in chapter 7, I don't have complete answers available for you that I'm going to put online, but I am going to put for labs, not lab 6 and 7, but on the chapter 6 and 7 content, where we're dealing with the Duncan data, okay, and then the interactions. I'm going to be putting some of my worked out answers online so you could, again, compare what you did as you're studying to what I said I think I like my answers, okay, to be. So with that in mind, any questions besides Daniel's, which I think was a really good one? A little bit more administrative, but sure, any question is a good question.
Yeah, sure. I got one. So could you just kind of go through and like run down, because I feel like this has been a little bit more like scattered than the first like set of content, like just kind of like all the topics that we've really like covered broadly.
Yeah, and I'm not going to do it in terms of this is the chapter where you find that, but rather here's a list of things that you probably would want to be aware of, and say I got that down. Okay, so topics list would include anything since chapter 4. Okay, no, anything since chapter 3. Okay, so if you review the general linear model, okay, so that's probably where I would start. Essentially, you're thinking multiple x variables are allowed, and if you have categorical variables, factors. Okay, we're going to highly leverage those things. Okay, so remembering the general linear model. We also talked about experimental design, okay, and then sequential and adjusted sums of squares. So maybe let's go with sequential sums of squares, and that gets us to adjusted sums of squares. Now, by default, the adjusted output is what JMP will give you. All stat packages give you adjusted sums of squares by default, with one exception. Okay, if you're using R as a stat package in some particular context where you have interactions, you get sometimes adjusted, okay? Sometimes it's going to be unadjusted, depending on the way most statisticians would usually prefer that. But by default, you get adjusted. And so you should ask yourself when going through a a problem on an exam, or when you're considering for your thesis research, what do I want to test? Always ask yourself, what do I want to control for? And are there things that I don't want to say, controlling for this? Here is my answer. And if you have some things that you do want to control for, but others not, maybe sequential sums of squares would be more appropriate to use. Okay? So what do you want to control for? If it's everything, adjusted. If it's only some of the things, sequential is the approach. Okay, so design of experiments, DOE, not Department of Energy, but design of experiments. And in design of experiments, the two concepts that we really leverage heavily are randomize treatments across the units which could have been assigned the treatment. Now that's pretty easy, if you have a collection of humans that you're treating one way or another, by flip of a coin or roll of a die is how the individual humans get the medication A, medication B, medication C, or medication D. But there's also in design of experiments the concept of blocking. Some things that you cannot randomize across, but you think should impact the outcome, you want to block on them. So take into account what block they're from. And now we key off of agricultural research in this content. So, we sometimes talk about split plot designs or something like that. The real notion is one portion of the field has one set of soil and temperature characteristics. A different portion of the field is a different. If you are doing work differently, you might block differently. In a past experiment with the people at the Dairy Products Technology Center, where I was involved in designing the experiment, these individuals wanted to make ice cream on different days and treat the ice cream in different ways. Maybe stir more air into it versus stir less air into it, add more whey, add less whey. Sometimes probiotics would be put in the ice cream. Other times maybe no probiotics would be put in. So those are all treatment issues. And so they're going to reconstitute from milk powder, they're going to reconstitute milk for the sake of making ice cream. Okay? And on humid days versus very dry days, the same dry weight of the milk product will literally be less milk versus more milk. So you have less of the actual milk solids, okay, on a very humid day, because if you weigh it out and you get 2 kilograms by weight of this powder, there's moisture inside of it. And that extra water on some days versus very little extra water on other days means you probably, if at all possible, would block on different humidity levels. And if that's hard to do, you block on the different days. Let's take two very different treatments and create base ice cream on the exact same day, and one half of the batch will be treated one way, the other half of a batch treated the other way. Block on things that you can't randomize across. Okay, so that's design of experiments, which we hit roughly in chapter 5. In chapter 6, it's quantitative and categorical variables. And in the regression context, it's always going to be some categorical variable, some quantitative variables, but if you add quantitative variables in, remember you have like maybe 2 or 3 or 4 regression lines. The additive model in chapter 6 says you have parallel lines, if you will. Or if you have quantitative x's only, you have a plane that we fit through the data. In chapter 7, we deal with interactions. And in interactions, it allows for the effect of one variable to depend on the level of a different one. In the categorical context, it's akin to design of experiments. You think the finger tapping data, for example, theobromide versus caffeine versus a placebo, and then do the people tap more or less? Well, some people just tap really quickly, even if trained to tap at the same rate. Some people will just tap more quickly, even without the stimulant. And with the stimulant, maybe it impacts them. They tap even more quickly than normal. Other people tap slowly by default. Even if you train them, they're going to tap fewer taps per 3-minute time period. Okay? So in this finger tapping experiment, or even the pigs experiment, the pig diet, this notion of an interaction is a possibility. What you block on may interact with your treatment. Or maybe you have two separate components of your treatment where they're non-additive impacts. I have the time of day that I leave from home to go into work. I have also the route choice. I have two choices. My treatment is two factors, route and then time. And the impact of the route that I take on the time of the commute depends on the time of day that I leave. The interaction model. Categorical, we have an interaction, effect, if you will. If you have a quantitative and categorical variables, one of each, you're saying we have different slopes for the different groups. In the general context of an interaction, you could even have, you could even have two x variables multiplied by each other, which takes that one flat plane and distorts it, so that way it's linear in each direction, but the overall plane as a whole does not look linear. It's a bent plane. It was flat, it's no longer flat. Or we could bend a plane to make it into sort of a parabola. If you've got a parabolic self-interaction, it's still an interaction. So those are the things that are on the test in chapter, those are the things that are on the test, but a review of the general linear models construct helps us put all those other parts into place. So I think that's a real quick summary, Harrison. Do you want to follow up on any of those?
Yeah. Sorry, what was the statistical term for when you're using planes? It's so the additive model is when you have the parallel regression lines, right?
Yeah, additive model is going to correspond to any situation where you really have no interaction term. And anything that says, oh, look, there's different slopes in the different groups, or there's an interaction effect, you would say a non-additive model. Now, I should be a little hesitant with a couple terms. One of the terms is general linear model. In our textbook, the term general linear model has one specific meaning. There are other meanings for the term as well. And so I should have warned you about that earlier. In that same sense, additive models, some people would say, oh, look, we're going to add in the interaction. Some people would still say a model with an interaction is an additive model. That's not our book's approach. That's not what I say in this class. But the term additive is one where if someone uses it, like the term general linear model, you should ask for clarification, because the distinct context in which you use these terms may have an impact on their meaning. It's like going into a different cultural situation and the word that you felt meant one thing all of a sudden means something else entirely different to that other group of people. Not always a problem. Sometimes it can be a big problem. Always check for context. Okay, anyone else want to follow up on this list of things to make sure you know? Okay, so let me sort of wrap up this thought on on these items. What are things that students tend to be most likely to trip up on an exam? Adjusted versus sequential sums of squares. That is one of those big deal issues. And then in the context of design of experiment, orthogonality. If you have orthogonal, then you have the ability to say the adjusted and sequential sums of squares results are identical, which has a real convenient result. The result is I never have to say, oh, controlling for these other variables. I simply say, yeah, there is an effect of this term. Okay, if you have orthogonality, utilize it. Okay, if you have a balanced design, you will get orthogonality, which means the sequential and adjusted sums of squares are the same. So we like orthogonality. The other thing that I think I do see students stumbling over sometimes is centering. Literally, if you center those interaction terms or center polynomial terms, remember, like if you subtract out the average value of a particular x for the slopes, it just messes up the calculations if you're doing it by hand. You can deselect the centering option in the analysis. So, but that gets towards the test and the mechanics of the test itself. I will provide to you any data set I used to generate the statistical output for your test. That's if I have it. If I don't have the raw data, I can't provide it to you. I'll just provide you the same summaries that I found and used myself. But if you know of a method via JMP that allows you to more quickly get an answer, go for it. That's absolutely fine. So let me just mention a quick way that you could replicate some of the work that you did in the lab on the Duncan data. Remember how you had the different slopes for the different groups? Different intercept slope combinations. You had to do algebra to get there. Another approach with JMP is you literally select just the blue collar group and you hide and exclude all the non-blue collar career types from the analysis and just fit a trend line, one trend line with fit y by x. You're done for the blue collar group. And then you would repeat that 2 times for the white collar and then the professional group. You don't literally have to do it the exact one way. Our book walks you through. Okay, if you can use the software, okay, to speed up your work, great. Okay, so the centering versus non-centering. When presenting to you a bit of output, I will either have made the choice to center or to not center based on the question as a whole and what's going to allow the typical student to best answer all of the questions that are stemming off of that one little stimulus, that one little chunk of output with, multiple questions attached to it. If you, by deselecting centering or by selecting it when I maybe had deselected myself, if you could get your answer better and quicker, go for it. Wouldn't bother me at all. I do know how to run these analyses myself, and if the result you want to present, just do a quick screenshot maybe even, and incorporate that into your answer, okay? Somehow, you could even include that in the file that you upload instead of putting into the text box portion of the output for your questions. That's fine. Works for me. Okay. It's been Harrison and I chatting for a bit. Anyone else got a question? Or should we go back to Harrison and see if he has another one? Okay, so what I'd like to do then is to do probably about 20-25 minutes worth of content and then turn you loose on the lab in chapters 8 and 9. And again, the lab from the 8 and 9 reinforces things that we've already done, okay, in a helpful way. So it's sort of intentionally although it's not on the exam to be tested, chapters 8 and 9, the lab activity will be beneficial for you as you prep for the exam. So I'm going to switch gears and show you something else now, and that is my desktop over here. And in chapters 8 and 9, what it boils down to is checking your residuals. How do we want to check them? Well, we look for things like normality. Well, done that. Equality of spread. Done that. Additivity. Well, that's a little bit more challenging, but additivity boils down to if I were to plot my residuals against an X variable, if I see curvature in the residuals against that X, I could either add a quadratic term into the model and make it better, or perhaps there's another approach that I'll show you in a little bit. Or another approach for additivity is if you have different groups where sometimes systematically some of the residuals are tending to be positive, but others are tending to be negative. That's a variable, a grouping variable, which could have, or better yet, should have been incorporated into your analysis originally. Okay, so the basic ideas are you know how to check Shapiro-Wilk for normality. Okay, I'm going to walk you through an example hopefully soon where we do that. And then if you graph the residuals against the predicted values or against individual X values, you could look for a lack of equality of spread, like we had done back the first time we looked at regression. Okay, and if we have some sort of a problem, we can fix it. Jumping down towards the bottom, if you see a problem, you do your best to check for those problems and then fix them, and then see if your fix worked. That's the nature of the lab today, checking for problems and fixing them. But what I'd like to do is to briefly take a diversion and focus on a collection of situations that go with the notion of these problems come in pairs. A lack of equality of spread tends to go with a lack of normality and a lack of linearity. So what do we do to tackle all of those situations? And I want to suggest a generic power transform approach. Okay? If you have the idea that instead of modeling the relationship between X and Y, hold on a second, darn it. I was trying to adjust my plane flights earlier that I'm going to be on in April. And so I called Orbitz, and for whatever reason, they said, yeah, we can't help you, so we're going to call you back. And I said, just don't call me between noon and 1, please. I talked to an actual human, and they said, yeah, no problem. I'll call you back in about an hour. And that was about an hour ago. And I'm thinking, I should have reemphasized the not between noon and 1, because I'm busy. But in case you were wondering, that's what happened. Okay, so refocus. In general, if you have an XY relationship and it's curved, you also have a problem with a lack of equality of spread. And you often will have a lack of normality. Okay, we're going to suggest, depending on the context, and you'll see the last page of the lab really does give you a list of situations, much like I'm about to explain and describe, a list of situations where you could sort of solve these sorts of problems with what I'll call a power transformation. Rather than modeling the relationship between X and Y, maybe in general, I could model a relationship between X and Y to some power phi. Or perhaps X to the power lambda and y to the power phi. In general, if you think that, thank you, Orbits, for calling back. In general, if you think that there's a relationship between this x and this y, the approach is, can I just re-express x? And can I re-express y and end up with something that seems linear in shape? I will call this section straightening out the scatter plot and fixing other problems. Okay, so in that regard, let's talk about our power transformation approach to life. If I were to make a scatter plot of x and its relationship with y, if the general pattern is linear, I'm happy. Yes? We're all happy, because we could do that with regression. If, however, the pattern is a little bit not quite perfectly linear, but the residuals are skewed right, I'm going to draw something like that. And by residuals skew right, I'm thinking for any level of x, okay, what do the residuals look like? Okay, for that lower value of x, if I see a skew right distribution of the residuals y, it's almost like, I would ask you to do this, but it actually works great if you're on an iPad. You could take the iPad and rotate it a little bit. Well, actually, in Zoom, maybe not. If you've got a computer and you could take your computer, rotate it, you could look and see a skewed to the something histogram. Okay? And for medium-sized x's, if indeed there's a distribution of the residuals, and for large x's, there's a distribution of the residuals, if you could see essentially in each of the, if you will, vertical lines for a particular value of x, if you see a distribution of the residuals which shows skewed. In this case, I would say positively skewed, because again, if you have a residual that corresponds to above what I would have expected it to be, it's stretching out to the right, okay? If I were to take this whole graph and rotate it 90 degrees, I'm going to have y, how do I rotate this 90 degrees? Okay, so y is going to be here, x is going to be this direction, and maybe I should erase that guy. So let's go forward. I had what looked like these, for the lower x's, a histogram of the corresponding y's. So for the low x's, I've got a histogram of the y's. For the medium-sized x's, I've got a histogram of the y values. For the large x's, a histogram of the y values. You're thinking, if that's the pattern you see, skew right, and skew right, you're definitely going to want to fix that skewness. How could we do it? Okay, I'm noticing also here, as our trend were increasing, I tried to draw it as though we have greater spread of the y's within any given range of x's, and also a slight curve. I'm trying to sort of show that slight curve here. A little bit harder to do now that we've rotated it. But if I have a slight problem, I could solve that problem maybe by transforming the value of y. So what sort of y transformations might help? Again, if you had a slight curvature here, and I'm going to plot x versus y, how could I change things up to make it look better? My conceptual thought is, if I could pull down the highest y values for the largest x's, pull them down a lot, but for the medium x's, pull the y's down only a bit, and for the small x's, only a tiny amount. Essentially, maybe that curved red trend will become straighter. So if my curved trend were all of a sudden straightened out, I feel good because I can do a linear regression now. So what sort of a thing would I want to do to y? Well, I'm thinking y to the power phi. And to pull the values of y down, I know that phi has to be less than 1. Okay, so phi less than 1 basically takes this sort of trend and bends it until it's linear. If you bend it the right amount, it will be perfectly linear. Okay, but it also has the pattern of, okay, let's even consider a possible value for phi. If phi equals 1/2, I think we're talking, hey, let's take a square root of y. Well, the square root of 100 is only 10, but the square root of 49 is 7. The square root of 36 is 6. The square root of 25 is 5. So there's a bending of that graph. Okay. And so if you're going to take a square root transformation of your y values, working in this graph in the upper right now, it's almost as though you're taking the large values and pulling them down a lot, small values only a little bit, large a lot, small a little bit, large a lot, small only a little bit. You're taking those red histograms and getting closer to normal. Not only do you get the normality now that maybe was lacking in the original graph, you also have the linearity that you would want to achieve. Also, look, it was wider for the larger x's, the distribution of the y's was wider than for the smaller x's. And now, with the blue histograms, things are more uniform in width. So values for phi that are less than 1 in classic ones are 1/2 and 0. They were sometimes called variance stabilizing transformations. Transformations, x-forms, if you will. So we're going to take the lack of equal spread and draw it closer to equal. We're going to take skewed residuals and get them closer to normal. We'll take some curvature and make it straight. So if you have a problem like that, transform the y variable. Take a square root, a 1/2 is the power. Or, and I think I mentioned this earlier this term, if you're talking about values for phi of 0, that really doesn't make sense because anything to the 0th power is just, 1. But if I approach in a calculus sense, in a limit sense, y to the tiny, and y to the even tinier, and y to the even smaller than that, if I have y to the power 0.1, then y to the power 0.01, then y to the power 0.001, then y to the power 0.0001, it looks as though I'm getting arbitrarily close to a natural log transformation as you approach y to the power 0 by getting powers that are closer and closer to 0, but from above, you have closer and closer to a natural log. So what we really say is, if you choose a value of phi being 0, you're just saying take a natural log. Other possibilities are a -1, I guess, -1/2. Okay, so that's 1 over the root of y, or even -1, which is just 1 over y. Those are even more extreme transformations. So the power phi really does dictate the nature of the transformation. Some books will even call this a power ladder set of transformations. So let's go ahead and do that. Clear the drawing and then go for the power ladder. Phi and then the various y to the phi. And so I think values for phi that are commonly used are 2, 1, well, that's no transformation at all, 1/2, 0, -1/2, -1. So that's y squared, y, don't transform it at all, root of y, the natural log of y, 1 over the root of y, and then just 1 over y. And some books will suggest, and I like to do this myself, but it's not necessary, if you've got a negative power, put a negative out in front of the 1. It just keeps the scaling such that what was larger is now still graphically larger further to the right along the y-axis. Not a requirement, but otherwise graphs will swap their x and y values. Not x and y values, but large x's become small and small x's become large, unless we do have that negative out front for values of phi less than 0. So this is just a power ladder for the y variable. Okay, let's consider 4 distinct possibilities. And what if that's your sort of graph that you're looking at? What if this is the graph you're looking at? What if this, or what if that? So if it's a nonlinear trend, it's going to be one of those 4, yeah? Because the only thing that doesn't follow one of these patterns... Actually, hold on. You're also maybe saying to yourself, well, what about that sort of a nonlinear trend? Sinusoidal, or, cubic or quartic. Well, there's other tricks we'll deal with next week to deal with cubics and quartics. For now, I'm just going to say if it's a monotonic trend that's nonlinear, it's one of these guys that's your friend over here on the right. Okay, so how do you fix it? Okay, I could either, for the upper left one, I could pull down the y's by phi less than 1, or I could pull down the x's by phi less than 1. X to the power phi and y to the power phi here. Reduce the power of x or reduce the power of y. Go with the square root, perhaps, or go with a natural log. The choice of which of these two I would choose to use depends on whether the residuals are skewed or not, and whether they have a lack of equality of spread. If the residuals are skewed and have a lack of equality of spread, transforming the y variable is the way to go. If the residuals are not skewed and don't have a lack of equality of spread, transforming the x variable is typically the first choice. And when I say the first choice, or typically the first choice, what I really mean here is there's multiple ways of doing it. And if you try to fix a problem and the fix doesn't perfectly work, you're going to try something else. The lab points you towards things that you would want to check for on the last page, but it's not a guarantee that it will solve every problem. So what about the lower left of these 4 graphs? I think y to the phi, where phi is less than 1, is going to pull down the y values. And if you pull down the very large y values a lot, the medium one's a medium amount and the small one's a small amount. It's like the example we started with. A value y to the phi is good, where phi is less than 1. Or, alternatively, I could take x and have x to the power, like I said earlier, let's go with x to the lambda. If I take the small y values and don't change them, small x values and don't change them, medium x's and change them a medium amount, and large x's, I change them a lot, I'm going to have straightened out the graph in the right way. X to the lambda, where lambda is greater than 1, will fix that sort of curvature problem. Or maybe a combination of both x and y transformations. So choosing x to some power and y to some power, as long as we're dealing with this lower left situation here, x goes up and y down, or x goes up or y goes down. One of those three will do it. Well, what about our upper right situation? Upper right situation, I think I could handle by drawing the y values up, the very low values for y, pull them upwards. Oh, or shoot, I could also take the very high values for y and pull those upwards. Either would straighten it out, yeah? Or if I were thinking maybe transform x, let's go with yellow to transform x. Let's take the values for x that are large and stretch them out. So I'm thinking maybe x to the lambda, where lambda is greater than 1, or y to the phi, where phi is greater than 1. Okay? So that's maybe the way I would pull that one off. Okay, so what about that lower right option of the 4 possibilities? In that lower right option, okay, you can sort of probably figure it out already, but stretching out the upper y's positively, or take the x's that are large and pull them down. So x to the lambda, where lambda is less than 1, okay, would be one approach, or transforming the y's by y to the phi, where phi is greater than 1. For the lower right approach, that should work okay. Okay. These solutions will straighten out your scatter plot appropriately, which is really the first key thing. Second, you should take the approach, choose a value for phi of y, the power of y, or maybe x to the power lambda, such that you end up with equality of spread and closer to normality. Okay? Straightening out your scatter plot, if you don't really pay attention to the residuals shape, the distribution of the residuals, or a lack of equality of spread, you can end up in a situation where you're breaking one thing as you attempt to fix another, which is sometimes called, when I try to fix my car myself. It's probably something I should go see the mechanic about. The reason is, if I try and fix it myself and break my car, that's bad. So if you end up feeling over your head at any point in time as you're working on your master's thesis, the Stat Consulting Service, we have a free consulting service where we tackle questions like this, where we help you out, making sure that you have done the appropriate analysis for your data. Often the question is, how should I transform my data to get closer to a method that will work with the data that I've been given? Okay, so this is a good place for me to stop and turn y'all loose that you could work away on the lab. So let's stop that share and put you in your lab groups, and you'll go work on a data set where it's trying to tackle a question about whether the size of an acorn, right, has something to do with the distribution of an oak species. When I say distribution, what I mean is, something like square miles, okay, of the home range. There are certain sorts of oak trees that are on the East Coast. There's some that are on the West Coast. They're a little bit different. I think the larger the oak tree, perhaps the larger the acorn. That's called gut feeling. I could be wrong about that, but maybe the size of the tree would matter. Maybe the size of the acorn is also related to the distribution, because if it's a larger acorn, it's less likely that a bird could carry it somewhere and drop it. Or maybe it's the other way around, and it's not something that's spread through birds, but rather spread through something like a pig could eat an acorn, and then after it goes through the lower GI tract, the pig excretes the acorn somewhere else. And the larger the acorn, the more likely the pig is to say, I want to eat that, and then run 20 miles and then poop it out, and then you have now a new oak tree in a new place. So the way the oak trees are going to spread within a species may be related to the size of the acorn. I want to know. But the fact that in California, microclimates have a huge impact, and the fact that on the East Coast there aren't so much microclimates that we worry about, I would think that whatever the impact is of the size of the acorn on the size of the range of the oak species, in California it's going to be different than we would find in Louisiana or Virginia or Maryland. Okay? So maybe there's two separate groups that we'll have to treat separately. So as you go into the lab, think about these things and work your way through, and we'll see where we get to. So let's put you in your breakout groups. And as always, I forget some of you where you're supposed to go to. But Jack, room 4, is that where you're supposed to be, really? And then who's in room 4 with Jack? Isabella?
Oh, me and Josh.
And Josh and Isabella also? Or Isabel, yeah. For Josh. I'm not seeing Josh. I'll see him, and Yu-Chen also will be assigned later. And then Ted goes to room 7. I know that. And then I know Daniel, you're in room 10 always? Okay. And then Adeline, where do you go to? I've forgotten.
I think 5.
Okay.
6.
6.
Okay.
6.
You're in 6. Okay. So I'm going to put those of you who've already sort of in Happy Land into your rooms. And then, yes, I will come and fix it. And the rest of you will be there shortly. So we'll see you soon. Okay, so I remember some of you where you're supposed to go to, but others I've forgotten. So if you don't get automatically put in the right place by me remembering, sorry, tell me where you're supposed to go to.
Me and Anise go to 6.
Got it. Who is the
I'm
me?
also going to 6.
Sharita 6?
Yes, thank you.
And who is me, Harrison?
Anise. Yeah.
Oh, she's there. Yu-Chen 4.
Maggie to 3.
Maggie 3. Got it.
Artika to 10.
10. Got it. Thank you. And Josh, where do you go to? I've forgotten. Yeah, 4. I can barely hear you, but 4. Orbit's called twice during class. Remember how I said don't call between noon and 1?
Yeah.
Yeah. Call me at 12:35 and 12:37.
Excellent.
And I don't know how to call that guy back. But maybe he could pull it off. Let's see.
Or Sagar, I'm calling from Orbit. Steven, can you pick up the phone? I'm on a call. I'm on a call with American Airlines. Thank you so much. Please pick up the phone.
Well, I said don't do it at that time.
Hi, this is Sagar. I'm calling from Orbit. Steven, can you pick up the phone? I'm on a call. I'm on a call with American Airlines. Thank you so much. Please pick up the phone.
Oh, why is this so complicated?
I don't know. He said that, yeah, Orbitz made the reservations, but American Airlines had locked them. So Orbitz wasn't able to make the changes, and they said, you know, you could call American. So I'm on the American callback list, and they said they'll call back about 3 ish. But I can't do anything till 2. Why is this so complicated? Because when I said don't call back during this time period, he heard call back in about an hour, apparently.
Well, it's weird to me that American Airlines locked it. And we have to go through all these freaking hoops.
And via the American Airlines website, they say, I'm sorry, we can't change it. I know. He wants to do something. Charlie, you want to go out? Come on. You want to go out? I can put you outside. Okay, right here. Check it out. Oh, what are you doing? I know.
You know what?
You said.
Kiana?
What?
Hello.
Hello. I like that.
Please don't. Good gosh.
That's a no thank you, huh?
Yes, no, thank you.
Do you want me to get out one of those meals that you could look at?
No, sorry.
This wood is getting dry slowly, but it's a lot lighter than it used to be. It used to be very heavy.
What are you talking about?
The lumber over here,
Yeah?
that we bought, because it was on sale,
Why are we buying lumber?
for the wall along the top of it, and for the steps. But we bought it right before, it rained. Or right after it rained, and then it was drying out, then it out front, then it rained on it again, so I brought it inside. You know what I'm gonna do tonight?
No?
I'm gonna grade some stat files from Smoky Kids while watching a TV show.
All right.
Because I don't literally have to be at the computer to do that.
Because they're not on. That's good.
The few that were turned in